Okay, so we're looking at the situation where we have a cylinder in the water and it's bobbing up and down in simple harmonic motion. Okay? Cross-sectional area is A, and the bottom of it is at some depth. Okay? So we know that the force is acting on this. Free body diagram, you know, this dot represents the cylinder, mass of the cylinder, whatever. You have mg acting down, force of gravity, and you have pressure times cross-sectional area acting up. Okay? So the point I've made here is you're not sure how to get the pressure. That's okay. I mean, it's not really, but because you should know this in physics, but not sure how to get the pressure, okay? But you know it's pressure times area is the force. So you get that much, and then you worry about what the pressure is. Don't worry about the effect of the pressure if you can't calculate the pressure. Write down the role of pressure in this situation, okay? So now all you got to do is figure out what the pressure is. Now, in physics class, and of course your book also tells you how to calculate the pressure, but it just tells you how to calculate it. It doesn't give you a reason for it. If you don't have a reason for it and you run into this problem again, you're stuck unless you got a Google chip in your head that allows you to instantly access Wikipedia as soon as you think the question. There's some people think that that's going to be feasible in about 5 years, which will make you obsolete. Unless you know how to think a little more deeply than just Google Wikipedia, okay? And I think you'll be fine with that, but you know, be prepared. You're going to be competing with other people who have those chips. I'm not sure it's going to happen in 5 years, but apparently we do have the technology to implant chips. The whole thing there is, can you like inject people's bloodstreams with pieces of chips that then go through the bloodstream and self-assemble themselves into a big chip in the brain? This is good. You talk about mechanical engineering, right? Well, get on it. Make that happen and be the first. You'll control us all. Not sure that's a good idea, but if I had to choose somebody, you would be near the top of my list. Okay. So anyhow, okay, here's cross-sectional area, A1, right? And this is an imaginary cylinder. Okay. So this cylinder, this imaginary cylinder just has water in it, right? And so it's got some dimension here, which we'll call H. Okay? So here you have the mass times gravity acting downward, right? Okay, well what's the mass? Well, the mass is density times A1 times H times G. Mass. There's a volume, there's a density. That's something you should be comfortable with. Now what's acting upward?
Well, the pressure.
Okay, well, what pressure?
The pressure on the bottom of the cylinder.
Anything else acting on this?
Well,
Any
there's
other forces?
the pressure on the top.
Yeah, I got the pressure on the top and the pressure on the bottom. So what you have then is
That's the last stuff you went through. I wish.
pressure on the bottom minus the pressure on the top, right? Okay? Well, this tells you that the pressure, I'll just call that delta P. Okay? This tells us then that delta P has to equal rho GH. I mean, look, this has to be equal to this because this water is not descending and it's not going up. Now, there might be circulation within, but whatever water happens to be within this thing, and we're going to just assume everything's stationary so we don't complicate it with turbulence and energy. Okay? That tells us delta pressure is rho GH. So, if we had a little cylinder, we'll put another shark over here just to be sure we know it's water. Okay, another cylinder here. One side at the top of the water, the other side down here, right? Then the pressure down here due to the water, well, there's no pressure up here due to the water, so the pressure down here has to be rho GH. Okay? And H would be the depth, because this is at the same level this is, right? So now we see this as rho GH times A. Okay? Now H is taken to be depth. And what I want to say then, this is, if we have a y-axis, okay, with y equal to 0 at the water surface, and we'll go ahead and put the y-axis upward, okay? So we're going to have a y-axis here. Y equals 0 here. So now, this is getting a little complicated, but here is the position y of the bottom of the cylinder. That's the word I was looking for. Okay? So y is the position of the bottom of the cylinder. Then this is going to equal negative rho GYA, because of course y is in the upward direction. So y is relative to the surface of the water. Okay? So when y is negative, you have a positive depth and a positive pressure. Okay? So keeping in mind that y here is negative. So now, net force is mg minus rho g y times A. Okay? Now, the mass of the entire cylinder, let's give the cylinder a dimension. We can't use H because we've already used that. So what's a good letter to use? Now I'm having as much trouble as I did trying to come up with cylinder. Every variable I think of, I don't like. So I'm just going to call it alpha. Okay? So, it's probably a bad connotation, but I'm going to use it anyway. So this is rho of the cylinder, and now we want to distinguish the density of the cylinder from the density of the water. Okay? So over here, I'll use W for water. There it is again, and there it needs to be. Okay? So you got rho of the cylinder times A alpha G minus rho of the water times G times Y times A. Okay? Now, of course, A is the same for both, so we got A times Okay, well, there's your net force. Okay? Make sense? So now, net force is mass times y double prime, right? So, well, the mass is just what it is here, right? Okay, so you have, and maybe I didn't need to factor out that A, because I'm going to have it here and it's going to do something. So that equals, yeah, I'm going to go back to this expression, probably won't end up using this one. Actually, no, I can use this one. It's going to divide out, okay. Now you can see what's developing. We're going to have a y double prime proportional to y. There's going to be a negative proportionality, which is going to give you simple harmonic motion. We're going to have this non-homogeneous term here if we're not careful. Okay? We get rid of that by taking the origin of our y-axis to be the center mass of the cylinder. We'll do that in a minute. I say that, I'm pretty sure that's going to happen. Till I work out the algebra, I'm never sure what's going to happen. Okay? And since I make mistakes doing the algebra, I don't know anything. But you know, let's pretend I do. Okay, so you have this. So we end up with y double prime. Now the a's divide out. I don't like to use that C word. I don't like to talk about cancel. Although I haven't noticed you guys making significant errors with it. I'm just, in pre-calculus, I don't allow the word. People cancel anything with anything.
How do you describe it then?
It divides out. It's a common factor. When you divide a common factor, you get 1 and you multiply 1 by anything. Well, 1's the identity. Okay? It's maybe a little steep for pre-calculus students, but cancellation's even worse. They will not learn the rules. They don't understand the rules of exponents, et cetera, et cetera. Okay? They come to us not knowing pre-algebra, even though they supposedly have the prerequisites for pre-calculus. Multiple measures. Okay, so anyhow, the rho alpha G, of course, matches this, right? So you get 1 minus rho W. Notice the G goes away. And you can think about physically why. Well, basically, the buoying force is supporting this thing in equilibrium. So it doesn't matter if you're on the Earth or on a planet of different mass that supports water. Okay? And you can think about why that is, and you should. Okay, so anyhow, the G divides out. Doesn't do that C thing, it divides out. Okay? And we're going to divide that then just by rho of the cylinder. Am I missing anything? Looks like I'm probably missing an alpha in the denominator, don't you think? And I'd better, because of course this would end up dimensionless. But this would have units of length. So now I have units of length divided by units of length. Remember, alpha is the height of the cylinder. So this is dimensionless, just like 1 is. Okay? Okay, well, That's a separable equation. Very easy to solve. Okay?
But it's a second order. What do you do
Oh yeah,
about
it's
that?
not, yeah, okay, it's second order, not second. Okay, it's non-homogeneous second order. Okay? So you got to get it, and you know, I was having trouble going forward with the idea that this thing's separable because I wasn't thinking. Looking down the road, I'm thinking, how's that going to work out? Okay, so it was beginning to dawn on me that it wasn't going to work out. So thanks for stopping that whole thought process, which would have led us who knows where. Okay, so we have this, right? So now it's separable. Your homogeneous solution is just going to be simple harmonic motion. And what's your non-homogeneous solution? Well, you work it out. And then work it out again. With the condition, well, with the idea that y equals 0 is your equilibrium point. That's the physics of what's going on. Go ahead and look again at the examples in your book. This is your restoring force. Okay? And think about what happens to this thing. Okay?